Hey, welcome back. Thank you for being here. In this video, I'm going to give you a little quiz about transformers. So this is the very first lesson in this program, and we cover the three architectures of transformers that we use in language modeling. You have the encoder-decoder style, which was the original one proposed in that paper, but then you have the encoder-only architecture used in natural language understanding task. The BERT model is a pretty famous example of that. And then the decoder only style, GPD models are, and all generative language models are under that category. So at the heart of it is a transformer architecture, right? So this quiz is about that. And in order to answer two simple but yet deep questions in this quiz, I hope you have read through the lesson, and also that you have read through the paper that was referenced, which is all you need is attention. So if you haven't and you don't want to spend too much time, go ask ChatGPT. I mean, I hope it gives you the right information, but go through it and then come back here and take this quiz. When I present the questions, I want you to pause the video and think about the answer, and then I'll get into my thoughts on answering that question. Okay? All right, let's get into it. So the two questions are going to be about the strengths and limitations of transformers. So, okay, let's see. First question. What makes transformers so powerful? What is the single most important idea in the transformer architecture that has led to this astounding success they've had, right? They're all pretty much widely adopted in all of modern AI. What is the core mechanism that led to that? What was the core innovation in the paper? So take a moment to think about it, and I will get into the answer. Okay, so what makes transformers so powerful is, well, the main idea is self-attention, right? So given a sequence of words or tokens, every token can pay attention to every other token in that sequence and draw its meaning based on that sequence, right? And it's the idea of like paying attention to everything that is given to it. So, all right, that sounds okay, but really self-attention can be created many different ways. What was the really brilliant part of the transformers architecture is the very ingenious way of achieving parallelization, right? So if you have a sequence of tokens, what they've achieved was the parallelization, like where you can have every token pay attention to every other token, but doing it in a parallelized manner. And that is really difficult to do in a sequential data, right? And what that has done is it has overcome the limitations of prior architectures like the recurrent neural networks, RNNs. They had to process one token at a time, and then even CNNs, which also go in a sequential manner. Now, that is what has led to the scalability, right? So we have models which have been trained on trillions of tokens, documents found on the internet, and you can achieve all the brilliant performance you see from large language models because of that scalability achieved through parallelization. So you have to really understand that part. And this could not be done with previous architectures. You could not have trained an RNN on trillion tokens. It's just not, we would be dying of old age before that RNN was able to be trained on that. And you have this modern 100 billion, 500 billion, even a trillion parameter large language model being created. That would just not be possible. So again, that's the core part, parallelization, that even though you're using thousands of GPUs, you can run all of this in parallel manner. Okay, so that's the core idea, and it's important to know that. Okay, now what are the limitations? What is it where transformers are deficient? So think about that as well. And my answer to this is that this almost feels like one of those Hollywood movies where you're like you're thinking about some powerful creature and you say, well, that's really powerful, and what's its weakness? And some brilliant person says, well, what makes it most powerful is also what makes it what's the core weakness. So yeah, the core idea of self-attention with the parallelization, there you have that, but you get quadratic complexity. Every token pays attention to every other token, and that is a huge problem, right? This is why we have a company like NVIDIA being the most valuable company in the world at the moment, shooting October 2025, and because they're selling these GPUs, right? That cost tens of thousands of dollars, and that is because of the enormous memory requirements of transformers. So yeah, quadratic complexity is a huge problem here, and that's because every token pays attention to every other token. Okay, now one other element here, which is this is where it gets into the strength is a weakness issue. So the way transformers handle sequence, right, is something called positional encoding, and it's really done in a when I first read about how positional encoding is achieved in that paper, the main paper, we talk about the sinusoidal kind of way of handling encoding positions of tokens. And I was like, really, that's what you do? That's the best way we can handle it. And really, that was a weakness. That is still a weakness. In fact, probably the largest area of research around transformers is how to handle the positional encodings better. And I feel like that's like you can't really solve it in the best possible, like in an optimal manner, because the core idea is to be able to encode to handle these tokens in parallel, which means every token is looking at every other token independently. Well, how do you then say this comes after that token versus that token, right? It's we can't have it both ways. And yeah, sure, maybe you can do better than the sinusoidal idea, and sure, there are better ideas, but it's always going to be a weakness of transformers. And I'll go one step further. I'm probably now presenting opinions rather than facts. This is my opinion. I think one thing that is validating this weakness quite a bit is one area of applications of transformers where they haven't outperformed other architectures is time series modeling. Okay, so time series data like forecasting. And forecasting obviously is where you have a sequence of numbers, right? And you have to think about it, well, why are transformers doing so well in modeling sequences of words, but not so well? They're not usually at the top of the performance in terms of benchmarks in time series forecasting use cases. It's surprising, you would think, but I don't think so. It's mainly because when you talk about language models and you take a word, they carry a lot of meaning, which also in a way represents position to the most part. So if you take a word like the word is, the verb to be, right? The word is. If I ask you where do you expect that word to be in a sequence, the possibilities are quite limited, right? So if it's a question, it's going to be at the beginning usually. If it's at the beginning, it's a question, right? If it starts, is this something? Or if it's in the middle of a sentence, it's usually going to follow another, like a noun, right? America is, pizza is. And so the word itself carries positional encoding meaning for the most part. So although transformers are handling the position in a weak manner, when it comes to tokens that in a way carry positional information, they're kind of overcoming that because of that. But if you look at time series modeling, if I give you say I have a time series of numbers and one of the numbers is 3, and I ask you, well, where do you expect that number to be in the sequence? It's like it could be anywhere, right? And that's a problem. So now you really need to be able to encode the position in the time series if you're giving it to transformers, and that's a challenge, right? Now, I'm quite aware there are foundational models in time series that are doing quite well. There's a model called Chronos, and there's a few other models, but I would still challenge it because it's like these are huge models that are being thrown at these time series models where data sets which are really quite tiny, and you're competing these hundreds of million parameter models against something that is quite smaller in size, and just throwing compute at it and saying, look, we're doing quite well, it just seems like overkill in my mind. So I've expressed some my own concerns here. So that's about positional encoding. The last part I will say here is about the black box nature of transformers. So if you take, you will look at the LLaMA 3 and other architectures or other models in this course or in this program, and they have layers after layers of attention blocks. And if you say, well, what's happening in block 1? What's happening in block 2? What actually is being learned? It's very hard to really figure that out. It works is all we can say. I know there's a lot of research around trying to put some explainability around these things, but it is very hard. It's just very hard to understand what's going on inside. Contrast that with something like RNNs used for image classification task. And you put these layers of convolutional layers, neurons, right? And you can see very clearly in image classification task or image related task, vision task, that maybe the first layers are detecting edges, the next layers are starting to detect shapes, and then the last layers are starting to put them together in detecting objects and so on. You can clearly see that when you analyze the activations of different neurons at different layers. You can't see that with transformers. And so explainability is a huge challenge because it just seemed to work like black boxes. Okay, so those are the trade-offs. I mentioned CNNs as a contrast. Again, maybe I'm taking a very specific narrow case like image classification, object detection, which has very heavy inductive biases in them, right? The CNNs were built for specifically for those kinds of tasks. So it's an unfair comparison, but yet if you're using these LLMs for planning, reasoning, various very important tasks, you would want to have some kind of explainability, which is very hard with transformers. Okay, so I will say the last point here, which is modern LLMs, especially transformers, succeed through scale. Not because there is something very inherently elegant about the architecture of transformers. So yeah, scale, right? This is, as I mentioned, NVIDIA is the most profitable or most valued company. It's because of the enormous compute requirements that transformers are causing. So that's just something I think you should be aware of as we go through this program. You will see this scale issue over and over. This whole program is going to, I feel like, talk about how do you work within the constraints of your GPUs, and the whole idea of LoRa and parameter efficient fine-tuning is about working within those constraints. That's the challenge, right? This is as much about learning techniques as it is about learning the engineering aspect, like working on cloud compute and trying to manage your memory requirements, how to fine-tune in the most elegant, most efficient manner so you don't incur a big cloud bill. It's not a problem specific to you, it's a problem specific to all companies. And so this whole program, because we are using transformers, a lot of it is about efficiency. All right. Okay, I hope that was insightful or at least helpful for you to just put some things in context. We'll see you in the next video. Thank you. Bye.